Hi, my name is Gabe Lewis, and I'm going to be talking about aircraft range and weight using Breguet's equation. And by the end of this video, you should understand the variables involved in determining an aircraft's range versus its weight, and also how to calculate an aircraft's range. So we're going to start off by looking at the four forces that act on an aircraft in flight. First, we have the lift from the aircraft's wings pulling it up, the thrust from the aircraft's engines pulling the plane forward, and then the air resistance or the drag that is pulling the plane backwards, and finally the weight of the aircraft pulling it towards the ground. And we're going to consider the case where the aircraft is in level flight at a constant speed. So the lift is going to equal its weight and the thrust is going to equal the drag. Okay, now we're going to define some important terms, starting with the range of the aircraft, which just designates the distance the aircraft can fly. We're going to call that R. The velocity of the aircraft, which is the change in the distance the aircraft can fly over time, so that's the derivative of r with respect to t. The specific fuel consumption, which is how much weight of fuel the aircraft consumes per hour of unit thrust from the engines. And finally the thrust, which is the pounds of force from the aircraft's engines. A very important concept here is that of specific range, which is simply the distance the aircraft can fly per unit weight of fuel consumed. And the equation for that is this: it equals simply the rate of change of the range of the aircraft, or distance it can fly, over the rate of change of fuel consumed. And if you recall, the rate of change of the range of the aircraft is simply its velocity, and the rate of change of fuel consumed from the last slide, we know that can simply be expressed as the specific fuel consumption times the thrust. So now we come to an expression of the aircraft's range, which is the change in the range is equal to the specific range times the amount of fuel consumed, so the change in fuel. And since we already know what the specific range is, what we're going to do is include an expression for the aircraft's weight through some algebraic manipulation. So if you recall, the amount of fuel consumed is equal to the specific fuel consumption times the thrust. But if you look at the thrust, since we're at constant speed and level flight, the thrust will equal the drag, and the drag can be expressed in this form, which includes L, and L equals the weight, so L is lift. And so if you put all that together, what you come out with is an expression for T, which includes the weight of the aircraft. So now we have the specific fuel consumption times T. It is now an expression which includes the weight of the aircraft, and that's included in the specific range. So now we're going to find a different expression for the velocity in the specific range that includes the aircraft's Mach number. So what we're going to do there is basically express the velocity in terms of A, which is the velocity of the aircraft, and now M, which is the Mach number. And so we already know that the specific fuel consumption times the thrust equals this new expression we came up with. So we're going to substitute all those in and come up with this new expression for the specific range, which, if you simplify it out, becomes this, which is the velocity of the aircraft over the specific fuel consumption times the Mach number times the lift over the aircraft's drag times the inverse of the aircraft's weight. Now, returning to our range equation, we have an expression for the specific range, and we know that the change in fuel weight of the aircraft is going to equal the overall change in weight of the aircraft, since it's the only weight that's actually changing on an aircraft in flight. So substituting that in, we have this expression, which includes the weight, the velocity, the lift and drag, and the Mach number, and specific fuel consumption of the aircraft. And if we integrate that, what we come up with is this expression, which is the velocity over the specific fuel consumption times the Mach number times the lift over the drag times the natural log of the initial weight of the aircraft divided by the final weight of the aircraft. So this is Breguet's equation for the range of an aircraft. So what we can do with that range equation is gain insight into the range of the aircraft as affected by the ratio of payload weight to fuel weight. So if you look at this graph, the range of the aircraft is on the x-axis and the payload is on the y-axis, and line segment A represents the maximum payload weight of the aircraft, but not necessarily all the weight the aircraft can hold, because we haven't got all our fuel. So towards the left is almost no fuel, which is very little range, and towards the right is more fuel, which is more range, until you reach the point where the aircraft cannot hold any more weight, and that's just because it has a lot of payload even though the fuel tanks are not fully filled, it can't take off if it were any heavier. So point C travels down that line further, except the payload weight has gone down and it has been replaced with fuel weight. So we have full fuel tanks now, not as much payload, but we still have the maximum weight of the aircraft, and you see the range actually increases. Now if we continue decreasing the payload weight with still full fuel weight, full fuel tanks, the range will slowly increase in the fashion shown in the graph there. So that's what we can do with Breguet's equation for the range of an aircraft versus its weight, and thank you for listening.